Okay, topic 3, AC machinery fundamental. So we have finished topic 1, which is just an introduction to the machinery principles. We have as discussed on the Faraday's law, Lenz's law that was related to electromagnetism, and then how that concept contribute to the something we call as a rotating magnetic field that is used that we use that concept to understand the working principle of the machines, such as transformer, uh, DC machine, simple DC machine. We have also studied about that. So now we are moving on the AC machinery, which is alternating current machine. Okay, so this is just a fundamental of AC machinery. uh, I would like to share my drawing canvas as well. Some notes that I've written here. I hope you can see this. All right. So in topic 3, basically this is the outline of the topic 3, AC machinery. So in the introductory part, basically I'll be discussing about some of the introduction on the AC machinery, in which for the AC machinery, basically we have two types of machine, which is one is the synchronous machine and the other one is the induction machine. So we will go more details on that later. But basically in this introductory part, we will be discussing only on the what is the difference between the AC machinery, between the synchronous machine and also the induction machine. Okay, and then in the introduction also I will show you some videos, which is some introductory videos of the AC machinery, induction, synchronous machine and also induction machine, and also the difference of synchronous machine versus the induction machine. And then in the second subtopic, in the second section, I'll be talking about a simple loop in a uniform magnetic field, which is basically something, the concept behind this, which is it is about this sort of figure, as you can see here. Okay, basically in a simple loop in a uniform magnetic field, we will be discussing on the concept of voltage that will be induced if we rotate this loop. Okay, this is the loop, the wire loop, and we have the uh, magnetic field, which is supplied by let's say this is a permanent magnet, north side of the permanent magnet, and then in the other side we have south side of the permanent magnet. So when we place this permanent magnet like this, it will produce B, which is the uniform magnetic field, which is uniform means identical in magnitude and also identical in the direction. Okay, constant in magnitude and constant in the direction. That is what it means by uniform magnetic field. So we place this loop, this wire loop, which is something that looks like this, in this uniform magnetic field. So we will derive some equation in terms of, for example, if we do the rotation of this loop, what is the voltage that is induced at the some of the at the segment, at the segment of each segment of this loop. We have some 4 segment here. Then we will calculate the total voltage that is induced between this terminal of the loop, right? So that is part 1. And then in part 2, the torque induced in a current carrying loop. So this is another concept of electric motor, which is if we supply the current through this loop, okay, passing through this loop, let's say counterclockwise direction, and then what happen is when there is a current carrying wire, the concept of current carrying wire, when we place it inside the magnetic field, what happen is that wire will experience some sort of force. Okay, the force will be induced, meaning that the force will be induced at these two segment, the two segment of this loop, which will automatically rotate this loop. Okay, then this loop also later will produce torque that will be further calculate the total torque acting on this, on all of this segment of this loop. Okay, all right, so that is part 2, which is section 3.2. Basically this is 3.2, this is 3.1. And then just a concept, another concept related to rotating magnetic field. Okay, so rotating magnetic field means that so far when you study about magnetic electromagnetism, we are talking about Faraday's law, Lenz's law, just a simple thing about electromagnetism. But this one is more to the magnetic field that is rotating, that contribute to the rotation of the rotor inside the machine. Okay, so this is the concept of rotating magnetic field, which is the base concept, the basics behind the working principle of a machine, like synchronous machine, induction machine, okay, DC machine, and so on. Then I will be talking about induced voltage in AC machine. So this one is much more focused on the actual machine, the real machine. Okay, for this one we just discuss the concept. Okay, for 3.2 we just discuss about the concept, how voltage is induced when we rotate that loop inside the uniform magnetic field, how torque will be developed if we supply the current to that loop. Okay, but for this one, the voltage and torque that is induced in the real construction of the machine. Okay, so basically we have to establish to understand the mathematical concept of these two, and then later we will proceed to this two. Okay, so 4 and 5 is about voltage and torque as well, but for the actual machine, which is the actual construction of machine. Okay, that's all we have in this topic. So basically we'll start with the introduction, right? Okay, this is the figure that shows the comparison between the AC synchronous machine and the AC induction machine. So we have two types of AC machine. Okay, the first type is, we call it as the synchronous machine, and the other type is induction machine. So how these two machines different to each other? Okay, so how synchronous machine different to induction machine and the other way around? Okay, so basically in theory, synchronous machine is for example, as you can see this, the rotor of the synchronous machine is supplied by DC power source. Okay, but for the induction machine, the rotor of the induction machine is not supplied by any source. There is no source, there is no need to supply any source. Maybe we don't have to supply current to the rotor of the uh, induction machine, because it works like a transformer action. So when we supply current to the stator, so it will automatically generate the rotating magnetic field around the stator, and then after that it will induce some voltage. Then that voltage will also make the current to flow inside this the rotor, so that after that the rotor also will be moving. Okay, not for the synchronous motor. Synchronous means the rotor speed is the same as the stator magnetic field speed. So I think we will have to look into some videos here we have to clearly understand what is the difference between the synchronous AC machinery versus the induction machine. Alright, so let me just share this video with you. Stop sharing now. Just wait a minute. Just allow me to play this video. Few seconds. Alright. I lost my browser. Where's my browser? So this is synchronous machine. So I'm gonna share this. Where is my share button? Okay, this. Alright, so I'm gonna share this video so that we can watch together. Optimize for motion and video, then share screen. Okay, so let us watch this video that shows the difference between synchronous motor and also the induction motor. Just okay. So if anything problem with the audio, just let me know. Let me just make this volume higher. Change. Okay.
AC electrical motor generally divided into two main categories. One, synchronous motor, and two, asynchronous motor. An asynchronous motor is popularly called as induction motor. An induction motor is an AC electric motor in which the electric current in the rotor needed to produce torque is obtained by electromagnetic induction from the magnet.
Okay, as you can see in the earlier part of the video here, we are comparing the synchronous motor, which is this one, with the asynchronous motor. Basically, another name for induction motor is the asynchronous motor. Okay, so this one is synchronous motor, AC machine, synchronous motor, and this one is asynchronous motor or induction motor. Right?
Popularly called as induction motor. An induction motor is an AC electric motor in which the electric current in the rotor needed to produce torque is obtained by electromagnetic induction from the magnetic field of the stator winding. An induction motor can therefore be made without electrical connection to the rotor. A synchronous electric motor is an AC motor in which, at steady state, the rotation of the shaft is synchronized with the frequency of the source current. The rotation period is exactly equal to an integral number of AC cycles. In this video, I will discuss the major differences between a synchronous motor and induction motor. Induction motor's construction is simpler, particularly in case of cage rotor. Synchronous motor's construction is complicated. An induction motor is a single excited machine. A synchronous motor is a doubly excited machine. Induction motor's stator winding is energized from an AC source. Synchronous motor's armature winding is energized from an AC source and its field winding from a DC source. If the load increased, the speed of the induction motor decreases. It is always less than the synchronous speed. Synchronous motor always runs at synchronous speed. The speed is dependent of load. Induction motor has self-starting torque. Synchronous motor is not self-starting. It has to be run up to synchronous speed by any means before it can be synchronized to AC supply. An induction motor operates only at a lagging power factor. At high loads, the power factor becomes very poor. A synchronous motor can be operated with lagging and leading power by changing its excitation. An induction motor is used for driving mechanical loads only. A synchronous motor can be used for power factor correction in addition to supplying torque to drive mechanical loads. Induction motor's efficiency is lesser than that of the synchronous motor of the same output and the voltage rating. Synchronous motor is more efficient than an induction motor of the same output and voltage rating. An induction motor is cheaper than the synchronous motor of the same output and voltage rating. A synchronous motor is costlier than an induction motor of the same output and voltage rating. Dear viewers, thanks for watching the video. If you have any question, write in the comment box. Don't forget to like and share. More updates, please subscribe to our channel Learning Engineering and get notification to press the bell icon.
Okay, so there are many differences that has been highlighted in that video about the difference between the synchronous motor and the induction motor. All right, as you can see, I hope that you can make some notes that show that remarks some difference between synchronous and induction motor. Okay, in terms of cost, in terms of construction, okay, in terms of source of that we supply to that machine, okay, in terms of speed, all right, in terms of synchronous speed, uh, sometime okay, the other point is related to the in terms of control concept, which is, for example, for the induction machine, the speed is not the same as the rotation speed of the electrical rotation speed. Okay, but for the synchronous machine, it is rotated at the same speed. The rotor rotates at the same speed of the rotating magnetic field supplied by the stator. Um, so another thing is in terms of starting. For example, induction machine has self-starting. Okay, self-starting, but the AC machine, it need to be started to using supply, okay, to the synchronous speed, which is the speed of rotor the same to the speed of the stator. Okay, after that it will synchronous. I mean that it will rotate at the same speed. So if we want to control the speed of that motor, basically we do the frequency based adjustment, meaning that we change the frequency. That means we change the speed of the motor. Okay, so that is the first video about the differences between the two types of HC machine, which is synchronous machine and also induction machine. uh, uh, so we have another video explanation, which is this one is about the video on the synchronous machine. Okay, I will play this video as well, but the response is quite slow. I think I'm not sure because there is it is not about the internet, it's not about the computer. I think, I don't know, the response is quite slow from my side. I'm not sure what happened to your side. Okay, let me just again play this video. So this is about the working principle of synchronous motor. All right,
Name suggests synchronous motors are capable of running at constant speed irrespective of the load acting on them. They are machines with high efficiency and are mainly used in high precision applications. The constant speed characteristic is achieved by interaction between a constant and rotating magnetic field. Rotor of synchronous motor produces constant magnetic field, and stator produces revolving magnetic field. The field coil of stator is excited by a three-phase AC supply. This will produce a revolving.
so basically we supply AC current, right? For example, the three-phase AC current we supply to the stator part, okay, the outside part of the machine, okay, which is the blue wire, red wire and yellow wire here, which is three-phase supply supplied to the stator part. But in synchronous machine, we are not only supply the stator part, but also we will need to supply the DC current to the rotor part. Okay, so both part, which is a rotor and stator, need to be supplied by the current. The difference is stator will be supplied by the AC current, but rotor will be supplied by the DC current to make this like a permanent magnet. Okay, just to make this like a permanent magnet, not something that revolving. It's not rotating magnetic field, but it is more to the making this rotor as a magnet. But this one, at the stator, we supply the AC current to make sure, because AC is alternating current, 360-degree rotation, right? Always rotating. The sinusoidal based concept of AC, sinusoidal current, that will produce the rotating magnetic field inside this stator. Okay, so that is why this stator is supplied by the AC current. But for the rotor, we can supply just the DC current, just to make sure that we can make this rotor as a permanent magnet. Okay.
Revolving magnetic field, which rotates at synchronous speed. Rotor is excited by a DC power supply, so it acts like a permanent magnet. Alternatively, rotor can also be made of permanent magnet. Interaction of rotor and RMF is interesting.
Okay, in a small motor, we can just use directly the permanent magnet. So when we use the permanent magnet, that means we don't have to give supply in terms of DC supply to the rotor. In a large machine, okay, a large synchronous machine, we will need to supply the DC current, because basically in real world we don't have that sort of a big magnet, right? So we have to make it a permanent magnet, which is using the windings like this. We supply this winding with the DC current to make this magnet, like a permanent magnet. Okay.
Assume you are giving an initial rotation to the rotor with same direction of RMF. You can see that opposite poles of RMF and rotor will attract each other, and they will get locked magnetically. This means that rotor will rotate the same speed of RMF, or
So it is mentioned RMF. Okay? RMF is basically this the rotating magnetic field here, okay, that is moving at the RMF speed. RMF, I forgot. Okay, so RMF mentioned here is basically referring to the yellow one. Okay, the yellow rotating magnetic field, and then the magnetic field from this rotor will align with the yellow one, with the rotating magnetic field, because north and south will attract to each other, making that something like it will stick moving. We keep moving according to the rotation of the magnetic field from the that is coming from the stator. Okay.
the rotor will rotate at synchronous speed. Synchronous speed can easily be derived as follows. This means that if one has got control over frequency of the electricity, speed of synchronous motor can.
Just remember, the RMF mentioned in this video is rotating magnetic field. The rotating magnetic field. RMS refers to rotating magnetic field, right? The acronym for the rotation magnetic field. Okay, I'm just
Very accurately controlled. But if the rotor has got no initial rotation, situation is quite different. North pole of the rotor will obviously get attracted by south pole of RMF and will start to move in the same direction. But since the rotor has got some inertia, this starting speed will be very low. By this time, south pole of RMF will be replaced by a north pole, so it will give repulsive force. As a net effect, rotor won't be able to start, or synchronous motors are not inherently self-starting. To make synchronous motors self-start, a squirrel cage arrangement is cleverly fitted through pole tips. At the starting, rotor field coils are not energized, so with revolving magnetic field, electricity is induced in squirrel cage bars, and rotor starts rotating just like an induction motor. When the rotor has achieved its maximum speed, rotor field coils are energized. So as discussed earlier, poles of rotor gets locked with poles of RMF and will start rotating at synchronous speed. When rotor rotates at synchronous speed, relative motion between squirrel cage and RMF is zero. This means zero current and force on squirrel cage bars. Thus, it will not affect synchronized operation of motor. Synchronous motors will produce constant speed irrespective of motor load only if the load is within the capability of motor. If external torque load is more than torque produced by the motor, it will slip out of synchronism and will come to rest. Low supply voltage and excitation voltage are other reasons of going out of synchronism. It is interesting to note that synchronous motor has got the same constructional features of an alternator. Synchronous motors also helps in improving overall power factor of the system. That's all about working of synchronous motors. Thank you.
So,
The rocket equation. It's a beautiful thing.
okay, that was the working principle of the
No
synchronous
astronaut
motor.
launches through space with their fingers crossed. That's not how we deal with risk.
Response is quite slow. I don't know. Suddenly I accidentally closed the another video that I'm going to show you, which is this one, the third video, which is video on induction motor. Video on induction motor, which is this one. The previous one was the video about the synchronous
like a
motor.
magnetic field of uniform strength rotating.
So, but this one is the video on the induction motor. So you can see the difference between the induction motor and also the synchronous motor. And in this video is quite good because it will end up with some application of the induction motor in real world, in real life situation. For example, we can use this induction motor in the fridge, in the in the electric cars, for example, uh, and also the air conditioning system. So as you can see in this electric car, for example, we can save some cost on the gearing because in the differential of the gearbox, because we don't need to design the gear that we can shift the speed. Okay, gear 1, gear 2, 3, 4, and so on, right? But we just can varying the frequency of the motor so that we can change the speed of the electric car. Okay, so that sort of things, the control in terms of speed, basically we control it in terms of electrical control, right, for the electric car, not the mechanical. So in electric car, most of the uh, working concept will be based on the electric principle. Okay, the machine that used in the electric car is more to the electrical machines, not the mechanical one, right? So I'm going to stop this sharing because it makes I'm going to change this to optimize text for image, optimize for text and image, and then share it again. Okay, there is no more videos that we can watch. So for today's session, I will start a little bit on this part. Okay, so we have finished the introduction, which is we had to watch some videos that introduce the differences between synchronous machine and also in the induction machine, and also some other explanation, detailed explanation in terms of video related to synchronous machine, and also the video related to induction motor. So from all of these three videos, I hope that you can watch again later to further understand the concept of or working principle of a synchronous machine and also the induction machine. Okay, now we'll be moving on a simple loop in a uniform magnetic field. Okay, so this is basically about the concept that we are going to establish related to AC machine. Okay, basically we are going to use this sort of arrangement. So as you can see in this my handwriting notes here, we have this arrangement of stator part, which is consists of the permanent magnet. Here is the permanent magnet. The other side, which is south side, also is a permanent magnet. And if we place this north side and south side of the permanent magnet, basically we can form a magnetic field that will cross this north from north to south, right? So this magnetic field, we assume it is a uniform magnetic field, which is in terms of magnitude and in terms of direction, it is uniform, it is constant, right? So we have this uniform magnetic field. Then what happen if we place this loop of wire, which is the construction of the loop is something like this. The rectangular shape of this loop is placed inside this magnetic field. Okay, so we are going to discuss on how to derive the voltage that is induced in every part of in every segment, every segment of this loop, wire loop. Then we calculate the total voltage that is induced in this entire section of this loop, right? So basically, when we have a look at this arrangement here, if you watch this from the back side, which is this. If you watch this from here, we can see something like this, right? Something like in this figure, which is this is the view from the back side of this loop, the wire loop. Okay, so we will see something like this, and this is another view which is from the top, I guess. Okay, from the top, which is from as you can see that I'm drawing now, which is from here. Okay, so we view this loop from top. We can see for this rectangular loop, wire loop here, you can see that it has some segment, which is AB segment, BC segment, and then CD segment, and another segment is D to A segment. Okay, we have 4 segments, okay, in this wire loop. So what happened if we place this wire loop inside the magnetic field and we rotate? Okay, we rotate this loop, this wire loop with omega m, which is the speed. Okay, the angular velocity of omega m. We rotate this wire loop counterclockwise direction. Okay, so from the concept, okay, if we rotate this wire loop, meaning that we move this wire loop inside the magnetic field. So if we move, or if we rotate this loop inside the magnetic field, what happen is the voltage will be induced at each of the segment of the loop. For example, we can see at segment AB, voltage EBA will be induced. Okay, and then at the segments DC, CD here, the voltage EDC will be induced. Okay, and so on. For segment BC, the voltage of ECD will be induced. So as the segment of D to A, the voltage of EDA will be induced. Okay, as you can see in this figure, at the segment of AB, all right, at the segment of AB here, EBA, right? At the segment of BC, we have let me just use another color. At the segment of BC, we have another voltage, which is ECB. Okay, so at the segment of CD, we have another voltage, EDC, and in this segment, we have voltage EAD. All right, so we have all four voltages will be developed at each of the segment when we rotate this loop, this wire loop inside the magnetic field. Okay, so we are going to derive, so what sort of we are going to derive the voltage induced at every segment. Okay, so basically we will start with this figure. As you can see in this figure, uh, we don't have much time. There are 4 minutes left. We have spent some more time. We have spent some more time on watching the video just now. Okay, just a little bit explanation about this. Okay, I hope that we can continue this on our next week session on Sunday, 8 o'clock, right? So basically, if you have a look at this from this view, which is at the back view, okay, you can see this part is AB segment. Okay, this left part is CD segment. So we rotate this wire loop. So basically, we have something like this. So this is AB segment, and this is CD segment. So we rotate this with the angular speed of omega m, right? We rotate this counterclockwise direction. Okay, so there is another variable which is at the AB segment. We have VAB. So VAB is velocity, the tangential speed, right? If we have something like this, the object that is rotating, it has the tangential speed. Okay, something like this. Yes. So we will have something like this. This is VCD. So V here is not voltage. This is the speed. Okay, which is we call it as a tangential speed. So we have the tangential speed that is measured at each of the segment AB and CD. Okay, so we rotate like this. So we can further extract this part, which is this AB part and CD part, into different figure here, as you can see in figure B and figure C. So at AB part, we see something like this. This is more to the vector, okay, vector analysis. Okay, so this is the vector at the vector of the velocity AB with respect to the direction or vector of the B, which is magnetic field. Okay, so vector of the magnetic field, as you can see, always showing to the right direction. So we don't have much time, only 1 minute left, so I think I will continue this in our next session. Okay, I will stop it now. So any question? Ada soalan tak, apa-apa nak tanya berkenaan kuis ataupun assessment lain? So kalau tak ada, saya akan stop lah untuk session hari ini, session sejam hari ini. So we'll see you again in another session, which is next week on 8 o'clock on Sunday. So next Sunday is as usual, right? No, there is no holiday on next Sunday. Alright. So okay, so see you then. Thank you.
Thank you, Doctor.
Okay, sama.
Thank you, Doctor.
Stop record.